Welcome to our EMEC341 final project. Let's get started. For our project, we decided to analyze a cheap H-frame 20-ton hydraulic press from Harbor Freight. We chose this hydraulic press because it had many poor reviews claiming it can't actually handle its 20-ton rating. Given that Harbor Freight is known for cheap tools, we wanted to investigate the legitimacy of these claims and see what the press can theoretically handle. We decided to analyze 3 types of failure. First, we looked at static failure to see how much tonnage the press could take assuming it's in perfect condition. We then also decided to look at cracked failure because Harbor Freight uses cheap materials and has poor quality control, so the existence of a crack is relatively likely. Finally, we decided to also look at fatigue failure because if you buy a hydraulic press, you're likely going to want to use it more than once without it failing.
We take a look at some of the assumptions that we've made. Although the table of the press is adjustable, for simplification, we will be analyzing the channels without the adjustment holes, and we'll be assuming that the horizontal crossbeams are perfectly rigid and will not deform. The only specifications on Harbor Freight's website give the material as steel, so we chose AISI 1020 steel for its malleability and thus ease of machining. It's often used in sheet metal applications, beams, and channels, which made it perfect for the vertical channels that we will be analyzing. As this product is not considered to be top of the line, the profit margin on it is likely low, and therefore it can be assumed that low quality steel was used, as is AISI 1020 steel. For analysis of fatigue, we will assume a state of constant amplitude of relaxed tension corresponding to the maximum rated load of 20,000 pounds as given for the press. As we were unable to find an exact K1C value for 1020 steel, we estimated from other steels, such as AISI 1144, as per the Dowling tables and other online resources such as MatWeb. Finally, for the analysis of brittle fracture, the C-channel will be flattened out and treated as a member with simple rectangular geometry so that we can correspond it to condition A within the Dowling table. For the material properties and dimensions, we used AISI 1020 steel. Most of these values were found in the Dowling tables or online resources such as MatWeb. However, we were unable to find an exact K1C value for 1020 steel, so we estimated from other steels such as AISI 1144, and we chose a value on the low side of fracture toughness for steels at 50 KSI inches to the 1/2 to reflect the assumed low quality of steel used.
Here we have the free body diagrams for the hydraulic press. We have a maximum design load of 40,000 pounds. And utilizing the symmetry of the H-frame, this load will be distributed equally between the 2 vertical supports. Thus, the failure analysis will be conducted on one support subject to a maximum tensile force of 20,000 pounds for both static and cyclic loading. Here we have our static failure analysis. So given the load of 20,000 pounds for each vertical support, the axial load was found to be 14.5 KSI, resulting in a reasonable safety factor of 3.5.
For the fatigue failure analysis of the H-frame, we assumed a constant amplitude loading of 7.27 KSI, corresponding to completely reverse loading of 7.73 KSI using the Morrissey relation. Using the property data of steel, it was found that the fatigue failure would be 3.11 times 10 to the 9 cycles, which corresponds to basically infinite life, and this makes sense as the reverse loading amplitude is well under that of the fatigue limit of steel. Our analysis of brittle fracture will be based on the assumption of poor quality control. As such, the C-channel making up the H-frame will be assumed to have a 6.25-inch crack spanning its middle section, and this geometry will be simplified to that of a rectangular cross-section for use of the Dowling tables. The K1C value is based on an average of multiple steels and then lowered slightly for the assumption that they're using the lowest quality steel possible, as they're likely saving money on the bill of materials here. Completing this analysis, the safety factor is found to be 0.84, which indicates failure via brittle crack propagation. It should be noted that the LEFM is verified here, as is visible in Table A2. In summary, it was found that the safety factor for static failure is 3.5. The product has an effectively infinite fatigue life of 3.11 times 10 to the 9 cycles, and assuming poor quality control and a large central crack, the H-frame will fail by brittle fracture. Thus, it can be concluded that the H-frame is likely not the source of failure, and based on the reviews, it seems the hydraulic jack is the most likely point of failure, and would make a good starting point for future analysis of this particular press.